This is the AB Fall Review multiple choice packet. This is problems 28 through 32. So if we look at number 28, it's limit as h approaches 0 of 1 plus h to the 6th minus 1 over h. This may be kind of tough to see, but this is in the form of a limit definition of a derivative. So this is what the limit definition of a derivative looks like. This represents f prime of x. So limit of, as h approaches 0, of f of x plus h minus f of x over h. This is essentially asking for f prime of 1 for the function f of x equals x to the 6th. Maybe kind of tough to tell, so I want to provide this these parts written out so we can kind of see a little bit better as to why this represents f prime of 1. So if we were to work this out from the very beginning, right, if this is x to the 6th, then we know that this is the limit definition of a derivative. And if we want to continue with this process, we would have to represent f of x plus h by plugging in x plus h into the x of the function. So that's represented by x plus h to the 6th minus the original function minus x to the 6th all over h. So this notation represents f prime of x. Okay. So if we know that, if we can tell that this is referring to the function of x to the 6th, then we don't have to work this all the way through. We can just go through a power rule, because if we know that this is asking for f prime of x for x to the 6th, then we also know that we have a much more efficient way of getting to the derivative, and that's by a power rule, which would be 6x to the 5th. Okay? However, this is going one step further. This is evaluating the derivative at 1. So if we were to take this one step further, right, if you were to evaluate f prime of 1, then that's the same thing as plugging in 1 in for all the x's, right? So if I replace x with 1, then this represents f prime of 1 for this particular function. Okay, so it's more of a conceptual problem to kind of see that, right? That this is referring to this function and is asking for us to evaluate this function's derivative at x equals 1. So if we know that this is talking about x to the 6th and asking about the derivative evaluated at 1, then we can go down this column, right? We know we're talking about the function x to the 6th. We find the derivative, 6x to the 5th power, and then we evaluate the derivative at 1. So 6 times 1 to the 5th is equal to 6, and that is what our answer is. Okay. Number 29, limit as h approaches 0 of cube root of 8 plus h minus 2 all over h. This is also in the form of limit definition of a derivative. So we need to kind of see that this is talking about the function cube root of x, and then asking us to evaluate this derivative, this function's derivative at x equals 8. So if we can see that this is referring to a limit definition and that it's asking for f prime of 8, then we can go through power rule and find the slope at that point. Okay, so this problem more fully worked out is given here. Okay, so if we can recognize that limit as h approaches 0 of cube root of 8 plus h minus 2 is really coming from this function cube root of x, and then just plugging in 8 to represent that derivative, then we can go down this column, right, and find the derivative going through power rule, bring down the 1/3, subtract 1 from the exponent, and then plugging in 8 into the derivative. So this is 3 times 8 to the 2/3. 8 to the 2/3 is the same thing as saying the cube root of 8 squared. So cube root of 8 is 2. 2 squared is 4. 3 times 4 is 12. So f prime of 8 is equal to 1/12. Okay, but it is presented in a way that is asking you to see the connection between this notation and that this is referring to the limit definition of a derivative. Number 30, suppose the limit as x approaches 0 of g of x minus g of 0 over x equals 1. Now this is in the form of the alternative form of derivative, which is f prime of c is equal to limit as x approaches c of f of x minus f of c all over x minus c. So if we were to do this for the function g of x evaluated at 0, then it would look something like this, right? Limit as x approaches 0 of g of x minus g of 0 over x minus 0, which is the same thing as just x. If we can see that this is talking about the derivative of this function at 1, then we can make that conclusion. Answer choice D, g prime of 0 is equal to 1. Okay, number 31. The function x to the 2/3 on the closed interval from -8 to 8 does not satisfy the condition for mean value theorem because, well, let's go through our conditions for mean value theorem. First is continuity. Okay? So between -8 and 8, there's no value that will cause this to be undefined. There's no variable in the denominator. And so our function is going to be continuous on the closed interval. Now, is it going to pass the differentiability test? That we have to find out by looking at the derivative. So if we find the derivative, which is going through power rule, 2/3 x to the -1/3, 2 over 3x to the 1/3. A function is not differentiable if there is an x value that causes the function's derivative or the slope to be undefined. And if we set the denominator of the derivative equal to 0, then we can find a point where the slope does not exist. And because the slope doesn't exist at x equals 0, and 0 affects the closed interval from -8 to 8, we can say that there's a sharp point where slope doesn't exist between our endpoints, which means that we can't guarantee a specific slope because the function has to be continuous and has to be a smooth curve where the slope exists everywhere. And because it doesn't pass the second condition, therefore our function is not differentiable at x equals 0, and we can say that f prime of 0 does not exist. And this is the cause of the differentiable condition not passing. Okay, number 32. If f of a equals f of b equals 0 and the function is continuous, then, well, this looks like these conditions look like Rolle's theorem, right? Because Rolle's theorem has continuity and it has endpoints being 0 or equal to each other. However, it's not quite Rolle's theorem because the second condition is missing. The second condition is the function is differentiable. So just because the function is continuous and the endpoints are the same y value is not enough to guarantee that we're getting a smooth curve, right? We could have this graph that is a result of these two conditions. And because we have a potential for a sharp point, then we can say that f prime may be different from 0 for all x on the closed interval AB, which means that doesn't mean that it can't be a smooth curve. However, we do need to take into consideration that this is a possibility based off of these two conditions alone. So f prime may be different from 0 for all x, and may be different can also mean where slope is undefined. Okay, if we look at the other choices, f of x must be identically 0. That's not necessarily true. We may have a function that have different y values. There exists at least one number, c, between a and b such that f prime c is equal to 0. We know this can't be necessarily true because the second condition of differentiability is not met, and so therefore we can't guarantee a slope of 0. F prime must exist for every x on the open interval. Not necessarily. Again, we're creating a condition that makes this a false statement. Okay? And f prime may be different from 0 for all x on the closed interval is the correct answer choice.